All right, these notes cover the conditions for regression inference, and these are the ones that are really quite tedious to check, but good news is it's really kind of the same pattern every single time. So well, you have 4 checks really. The first one is that you want to check that your repeated responses of Y are independent. So basically, repeated observations on the same individual are not allowed, and that would hopefully be kind of obvious if it happened in the problem, because if you measure something twice on one person, obviously those won't be independent measurements. So that's just something that you kind of assume that they are independent. The second check is the mean response has a straight line relationship with Y. So basically, you want to make sure you could do, the first obvious thing, of course, is to graph your data to see if it's a straight line relationship. However, unfortunately, a lot of times something that appears to be a straight line relationship is actually not. So while that's important, and I shouldn't cross that out, I mean, you definitely want to do that, but more importantly is you want to check your residual plot. And if you haven't watched the first video, I walked through how to make a residual plot, so you should watch that because I'm not going to talk about it again. But you check the residual plot, and of course your residual plot should show a random scatter. And if it shows a random scatter, then you know that your relationship is a straight line relationship. The third assumption is you want to check that the standard deviation of Y is the same for all values of X. And this is the one that tends to not usually be met, actually, but we kind of go with it anyway. So you, again, look at your residual plot. So good news is you've already done the residual plot for the second check, but what you reference is different. So the residual plot here shows you if you have a straight line relationship through that random scatter. Then here your residual plot, you want to check for an even amount of spread. And again, usually doesn't happen. So for example, if your scatter plot is relatively, even amount of spread, and then all of a sudden it starts to grow in terms of your spread, that's not ideal, but usually that's the check that doesn't get met. So check it. Hopefully, maybe it'll work out. Then the last check is for any fixed value of X, the response variable Y should vary according to the normal distribution. So here, you're going to want to plot your residuals, not to be confused with doing a residual plot. Okay, so you want to plot your residuals either with a histogram, you could do a stem plot, you could do a box plot, you could do a normal probability plot, but basically you want to check, you don't want outliers, very little skew, if any. That kind of relationship is what you're looking for, and then you know that any fixed value of X will vary normally. So to recap, the first one, just make sure your observations are independent, and again, we kind of assume that unless we have reason to believe it's not. And then you look at the residual plot for a random scatter. That tells you have a straight line relationship. Check the residual plot for even spread, which this is not showing, so that your standard deviation is the same. And then plot all of your residuals, either with the histogram stem plot, to look for normality. All right, then something that you probably won't have to actually calculate by hand, but you'll have to recognize it, is how to find the standard deviation for a least squared regression line. What it does, however, the standard deviation for a least squared regression line describes the variability of the response variable Y about the true regression line. So basically, how spread out are your data points from that regression line. So ideal to have a small standard deviation, of course. Mathematically, and this is on your formula sheet, nothing you have to memorize, but the standard error about the line, which is standard deviation, is the sum of all of your residuals squared, so nothing will be negative, divided by n minus 2, and then you square root that. And of course your residuals are all your Y values minus the predicted Y values, so that's just plugging in the formula. Then your confidence interval for the regression slope is your estimate plus or minus your critical value times the standard deviation of the slope. So of course, since we're dealing with slope, your estimate would be B. Your critical value is T star, which you're familiar with, and that's, again, a t distribution and not a z distribution. And then the standard error of your slope, which is denoted down here, is on your formula sheet also, is S, which I just talked about, the standard deviation of your line, divided by the sum of x minus x bar quantities squared. Now this you won't have to calculate. The standard error calculation will either be given to you or you can find from your calculator. The other thing to note is your degrees of freedom for confidence intervals of slope is n minus 2 instead of n minus 1. So for the most part, the regression information that you have to deal with in terms of inference is computer output information. So the first video I talked about IQ score versus how much an infant cries. So go back and look at that if you want more information on the problem. But here is the computer output of that information, and notice it says the regression equation is IQ equals 91.3 plus 1.49 times cry count. So this value is definitely your y-intercept, and then this is definitely your slope because it accompanies your variable. So in other words, you know, y hat equals 91.3 plus 1.49 times x, but instead of using y hat and x, they define y as your IQ score and x would be your cry count. Now, how you get, like if they left these blank, how you get these constants down here is the word constant literally means that. So you know that your y-intercept is just a constant. There's no variable by that. So that constant and then coefficient, of course, is a number in front of a variable. So if it's a constant, the coefficient for that constant is 91.268. That's your y-intercept. Okay, so that value is your y-intercept because it's labeled as your constant coefficient. Below that is cry count. So here's a contextual piece. So how much does the baby cry? The coefficient of that is 1.492, and that is going to be then your slope because that's what varies because it's not constant, right? Of course, depending on the problem, that variable will be different. So you can get the equation based off that. Then notice other things like S. That estimates your sigma, so that will be the standard deviation of your line, so 17.5. Then over here, not to be confused with standard deviation of each individual piece. So this is the standard deviation of your y-intercept, and this is the standard deviation of your slope. And then you have test statistics and p-values for both your y-intercept and your slope. So notice here, the standard deviation for my slope, that's what you need for your confidence interval. That's the standard deviation sub b, so standard deviation for your slope. We usually don't run inference on your y-intercept because it's just not useful because your y-intercept is so often unpredictable. So, however, we might take a look at that in a little bit. So let's utilize what we talked about now. Okay, so here's a printout, and this is talking about how tall you are versus the length of your arm span. So the first question says, what is the slope of the regression line? And then interpret that slope. So notice up here you have height equals 16.4 plus 7.767 times your arm span. So I know that the constant coefficient is my y-intercept, but they kind of gave that to you up here. And the coefficient for my arm span is going to be my slope, again, kind of given up there. So what is the slope? Well, that's obviously the 0.767. And then remind yourself that slope is the change in y, the average change in y for every increase in x. So y would be your height. So this means my slope interpretation would be your height goes up 0.767. I guess I don't know what this is. I'll just say units because I don't know what those units are. On average, my height goes up 0.767 units on average for each 1 unit of arm span. And again, I don't know what they're measuring this in, so I'm just using the word unit versus inches or feet, you know, that kind of thing. So that's my interpretation. Number 2 says, what is the standard error of the residuals? Okay, it's not the standard deviation or the standard error of your slope or your y-intercept. It's just of your residuals, and that's always this S value. And the interpretation for that is, well, it's the spread of the residuals about your least squared regression line. And of course, we want to keep that small if possible. Then number 3 says, what's the standard error of the slope? Okay, so standard error of the slope instead of the residuals. So I go to my slope, which is arm span, and the standard deviation of that is that 0.08116. And interpret that, so that would be the spread. The standard error of the slope is the spread of my slope values. All right, and then number 4 says, do the data strongly indicate a linear relationship between x and y? So a strong linear relationship, well, lots of things play into that. We don't have any graphs to look at, so we want to probably look at r and r squared. And you don't want to use the r squared adjusted there, but my r squared is 84.8%, which means if I take the square root of that, my r will be 0.92. And I know that's positive because my slope is positive, so just be careful about that. But yes, does it, well, according to that, yes, it shows a strong linear relationship. So I'm going to write that out, strong positive, because my slope is positive, linear relationship, although technically without graphing anything, this could be completely off. So based off of my r and r squared, yes, this is good. And the 5th question finally says, find a 95% confidence interval for the true slope beta. So remind yourself that your confidence interval is your estimate, which for slope would be b, plus or minus your critical value times the standard deviation of your slope. So good news for us is we've got everything we need on the computer output here. So our slope is the 0.76722 plus or minus our critical value. Remind yourself you find t star by doing inverse t, and since I'm 95% confident, I would do 0.95 plus 1 cut in half, so that's 0.975. And degrees of freedom is your sample size minus 2. And, oh, I neglected to give you your sample size. Sorry. Well, you had 18 data points. I'll just squeeze that up here. This would obviously be something you would not have to guess. So 18 minus 2 is 16. And t star from there is 2.12. So there's your critical value. And then the standard error of the slope, again, standard deviation for slope, which is given, and that's 0.08116. And then if you dump that all on your calculator, you get from 0.6 through 0.94 as an estimate for beta. So we are, if I can squeeze in my conclusion, 95% confident that the true slope of the least squared regression line between, bring in some context here, arm span and, let me scooch this up a bit, between arm span and height is between 0.6 and 0.94. Okay, or since we're talking about slope, you could also say for every 1 inch, I'm going to assume these are inches, for every 1 inch change in arm span, the predicted height changes between 0.6 and 0.94 inches on average. So to me, the last statement is probably makes more sense, but you could do either one. The last thing I would clarify is you can do this process on your calculator, and I'll just squeeze this in here. Actually, I'll squeeze it up a little bit more by doing the linear regression t-interval on your calculator, and it'll prompt you for your slope, which was again given, and it'll prompt you for your confidence level, and then it will give you this outcome. So you should be able to show this, but then if you go from here to here, that's totally fine if you want to use your calculator at that point.